No, there's no pattern for the ortho and meta. They're going to be more, okay, let's look at the example on the NMR handout, the warm-up page. Warm-up page right here, very important. I could ask a follow-up question. Number 5, 1, 2, there's 6 here. Okay, disubstituted aromatic rings. And it's important to know how many signals, okay? But also, what would the signals be? Singlets, doublets, triplets, etc. Of these 6, how many would just give 2 signals?
3 of them?
Also, there's a difference between if the substituents are the same or different. Because you can't just say 2 substituents and have the answer. If they're the same substituents, then you're going to get a different answer than if it's different substituents. So, for example, here there's only 2 signals.
Yeah.
But here there's 4 signals. We're doing proton NMR. Okay? Proton NMR. Well, we're doing both. Proton NMR. We'll do H and then carbon. H, let's just do 2 signals. But this one's 4. Because all 4 H's are different here. Here, this H and this H are the same. This H and that H are the same. 2 signals. 4. How many signals here? That one, and that one. 3. Yes. Here, all 4 are different. My first question was, how many of these will give just 2 signals? So far, only this one. How about over here? How many signals for this? Proton NMR?
2.
1. All 4 H's on that ring are the same because of symmetry, double symmetry. This H and, for example, that H are the same. This one is right next to a bromine and 2 away from the bromine. We call this ortho to this bromine and meta to this bromine. That's the same thing. Ortho to a bromine, meta to a bromine. They're the same. And if you look at all 4, they're all the same. 1 signal. How about this one?
4.
2. These 2 H's are the same. They're both ortho to the bromine. These 2 H's are the same. They're both ortho to the fluorine. And meta to the bromine. 2. Original question, how many of these will give just 2 signals?
2.
1 on each end. 2. Okay. Now theoretically, this would give what I said. What would these 2 signals be? Let's just draw the H's. That's HA. That's A prime. This is HB. That's B prime. There are your 2 signals. The other is just the same signal. It just makes the integration for 2 instead of 1. Will this be singlet, doublet, triplet, what?
Doublet.
Yes. This is doublet. How many H's?
1.
It's doublet 2H. What is this?
Doublet.
Also doublet 2H. Why is it a doublet? It's got 1 H next door. And plus 1 is 2. Doublet. Question?
Well, this is that last problem you worked on the video. I was wondering why this other structure wouldn't be it. Because
This one here?
no, and the actual like the
Right. Why would it not be? Why would it
you
not be what?
you worked the problem from that pre-class NMR, I mean the NMR sheet or the yellow one that you gave out, and I was wondering why this other structure wouldn't be it when it still has the same like.
That's why I was trying to clarify. What do you mean by it?
Because you drew it where it was the ether and then ethyl, and then the carbon attached with the OH group attached to it. With the why wouldn't it just be why couldn't it be a CH2 group with an ether group and then the ethyl and then OH on the other side?
I'd have to see your structure. Is that the one where I was trying to think of another structure?
Yes.
While I was doing it?
Yeah.
It seemed like there was something else that could have been. But I thought you were talking about this though.
No, so,
Okay, this is something else.
yeah, why couldn't you leave the top structure?
Okay, that's, can I show this on the overhead?
Yes, sir.
That's all you got? You don't have any, where'd you work the problem at?
I was thinking about it quickly because I was having that problem when doing the worksheet over the break, and because I was getting through.
Yeah, that is the other structure that I was trying to come up with. It's very close. The CH2 would be perhaps a little bit more downfield because it's between oxygen and the benzyl and the benzene ring. The key difference is one of your answers is an alcohol, the other is a phenol. There could be a chemical test to distinguish between those. I'm not sure that the phenol is going to give a positive Jones oxidation test.
Oh, okay, that's, yeah.
But it's very close, and that's actually the one I was trying to come up with. Back to this here. Okay. Everybody agree? Doublet 2H, doublet 2H?
Yes. Will the doublet 2H's for the ortho look any different on the NMR than the para doublet 2H's?
We'll get to that.
Okay.
Question?
Why wouldn't the HB be a triplet if there's a hydrogen on the top and on the bottom of it?
Well, this H is the same. That's HB prime.
So that would make it a doublet.
This is HA prime. These H's are the same, these H's are the same.
Okay, so it doesn't matter that it's between two H's as long as one is the same, then it's still
Identical H's don't split each other.
Okay.
Because that's the signal.
Mm-hmm.
A signal don't split itself. Good.
Okay, thank you.
This is not, this is one signal. That signal is experiencing a neighbor. It's a little, you have to think about it, just take the fact that identical H's don't split each other. That H is the same as that one, so it ain't going to split. This is one signal. Whenever you do looking for splitting and it has symmetry, just work with 1/2 of your symmetry. Okay? That's why I didn't even draw this. The only place you're going to see this here, these two, is in your integration. That's why it's 2H instead of 1H. Because there's actually 2 of them. There's another. But for your splitting, just ignore your other side of your symmetry, and you'll be good.
Thank you.
Okay, the other question is down here. That's a pair of doublets. This is also a pair of doublets, okay? Because this is HA, and this is HB, and this is HA prime and B prime. Yeah, a pair of doublets. Okay, that's what we got here. It's 2H, 2H. Yeah. Yes, theoretically, a pair of doublets, which I said is classical for what? Para-substituted benzene ring. But when the groups are different, because if they're the same, you're not going to get a pair of doublets. You're only going to get one singlet. That would just be a singlet, because they're all identical. Identical H's don't split each other. A pair of doublets, 2H, 2H, is classical for para-substituted. Of course, the groups are different. Yes, theoretically, it could be this. But the substituents have to be the same for it to be this. And you can easily see that when your substituents are not going to be the same. In the one I worked, we only had one OH group. So if one OH group is here, then obviously it can't be here. Then they're not the same. So yes, this is very odd, rare. Classical pair of doublets, usually para-substitute, para-disubstitute. Okay? All these others are going to give, what would these 3 look like? Well, it's more than 2, but they tend to also be sort of, well, I reckon they could be doublets. Let's not get into that. Pair doublets. Pair meaning two, right? A pair, classical. And you got to be careful. Sometimes this will not be a pair of doublets. So you can't in reverse say, hey, it's not a pair of doublets, so it's not this. You can always do that.
Why wouldn't it be a pair?
If these two groups are different, but they're so close that it doesn't make the peaks separate enough. And they may be just on top of each other.
Overlapping.
And it may look like a multiplet when it's really a pair of substitute. It's because the pair of doublets didn't separate enough.
How do we know if that's the case?
There'll be plenty of other ways to tell. Okay? Plenty of other ways to tell. For example, carbon and NMR. Okay. What is very tough to tell is actually the other. Ortho and meta can be hard to distinguish. Pair is often easier to distinguish somehow. Okay? How will we tell? There's plenty of things we can do where it would be very difficult to tell. So you have to just trust that I'm not going to take this that far. Okay? What we're doing, okay? Okay, good. Ozonolysis. See how we did on these here. There's a large number of advanced NMR techniques. Why are those techniques? Why were they needed? Why did chemists develop those techniques? Because simple NMR often doesn't give you all your answers. Okay? Looks like we're doing ozonolysis. Yeah, ozone followed by a magic step. What does that do to alkene? Cleaves the alkene. Each carbon becomes a
Carbonyl.
Okay, so there's a little memorization prompting. Okay, then your knowledge kicks in. Can I just cleave this and call this phenyl? And the carbon here becomes carbonyl. What else is on this carbon?
A hydrogen.
Yes, just an H. Since it's aldehyde, I like to draw in the H. I recommend you do it as well. The other carbon, boom, to a carbonyl. What else is on this carbon?
An H.
Also just an H. We get two aldehydes. Are the aldehydes going to survive?
Yes.
Yes.
Yeah. Yes, there you go. Two products, two organic products, both aldehydes. Down here, ozonolysis, magic step. Can we cleave the alkene?
Yeah.
Boom, boom. This becomes carbonyl. Boom, boom, boom. And down here, this becomes carbonyl. That carbonyl carbon has a methyl. What does this carbonyl carbon have?
Hydrogen.
H. It's connected. Two carbonyls, but it's connected. So it's one molecule that has two carbonyls. Looks right? Well, 6 carbons total. Going backwards, what starting material would give those two products upon doing an ozonolysis? And now this is kind of generic here, but typically in ozonolysis it starts with an alkene. Alkene is what you would do in ozonolysis on. So anybody got the alkene? Well, this carbon used to be bonded to this carbon. This carbon has two ethyls, and the other carbon has a phenyl and an H. Well, it's there. If you draw a carbon, you should draw an H. There it is. We can draw this more line bond and go boop, 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 boop. Same thing. Do we have to worry about stereochemistry here?
No.
About the alkene? I mean, there's is this alkene stereogenic? Do we need to worry about cis or, E or Z?
No.
No, the alkene's not stereogenic. By the way, does stereochemistry of the alkene matter? No. In the very top example up there, we have the trans, the phenyl and methyl are trans. If they were cis, you would get the same exact products. Once the double bond is cleaved, it's the same thing. In this case, there is no stereochemistry. If we put the phenyl here, it's the same thing, so we don't even have to think about it. Right? Wouldn't this cleave to give those two? Yeah, there's your product. That's a very common question going backwards. I think there's one like that in the workbook. So it's one of the top 10 reactions in organic chemistry. It was on that alkene puzzle. I gave you an organic 1. I sent you twice an organic 1. I've actually now given it to you twice here. One to the handout. I sent it to you by email. And so now you can try that one on that puzzle where in organic 1 we said to omit it. There's an ozonolysis procedure here, if you want to read about that. In this example, though, the ozonolysis product actually further reacts. By an aldol reaction, we'll see this this further reaction later in the course when we cover aldol reactions. But when you're looking at it, just consider this part here, this going to this. If you're interested in reading about how it's actually done, this comes from a periodical called Organic Syntheses. It's been published for 100 years. It used to be subscription, but about 20 years ago they made it free. And now you can access all these procedures online. Any reaction we've ever covered, you can probably find an exact procedure on so-called OrgSyn. There's a search engine. And you can see how you actually do some reactions. For example, of course, there's a million type of reactions have been done, but you can find an exact example. These procedures are submitted, but they're also checked before they're published. Checked by some other chemist to confirm that they're good procedures and that they work as written, etc. So more of the practical side of things there. Over here is a drug synthesis. It's not an ozonolysis, but remember we can do the same thing sort of stepwise. I think this is Zoloft. There's a synthesis here. To make a cyclopropane. We don't know this chemistry. It's actually it's a carbene, but it's a different way to make carbene than the way we did in organic 1. From here, then they react this 2 steps. The B is what we want to focus on, so I'm having to show it separately. If you look at what they have here, they still have the methyl ester, but this carbon is now a carboxylic acid. What they've done here is they've cleaved this alkene. carbon, and this carbon has become carboxylic acid. If you did this by ozonolysis, what would this carbon become?
Aldehyde.
It would become an aldehyde because there's an H there. All they're doing is just oxidizing the aldehyde in the same process. How are they doing it? Not with ozonolysis. B. Now this is a common way is to show it with the letters B. KMNO4. What would that do to an alkene? Well, if you heat it, it'll cleave it and give the carboxylic acid. They're doing it with KMNO4, and they're including sodium periodate. The way I showed you, this can convert to the diol, and that'll cleave the diol to the 2 carbonyls. But since KMNO4 there, what will happen to the aldehyde?
It will just completely
Oxidized to carboxylic acid.
It becomes a carboxylic acid. They're using T-butanol and water as solvent. Water to help dissolve these salts, or T-butanol is an organic solvent to help dissolve the organic. It's an alcohol, but it's T-butanol. Why do you think they use T-butanol and not like ethanol?
It's more
T-butanol can be oxidized.
Sir Rodney?
T-butanol can be oxidized.
Yes, T-butanol cannot be oxidized by KMNO4. If you use ethanol, KMNO4 is going to oxidize your solvent, and you're going to be doing chemistry you don't want to be doing, and it's like it's going to consume your KMNO4, and KMNO4 may not react with your alkene. You want your solvent to be more inert. T-butanol is a common solvent. So it's going to be inert to being oxidized, at least in this class and under those conditions, yes. Half an hour room temperature, okay. Then from there, they've got this carboxylic acid. They treat it with base C, dimethyl sulfate, and what base? Potassium carbonate. The base makes the anion of the carboxylic acid, and then they come in with dimethyl sulfate. Remember dimethyl sulfate? It's a dimethyl ester of sulfuric acid, and the anion attacks the methyl, kicks off that, and then they have O-methyl. And so that's how they end up with both of them being methyl esters. They just do an O-alkylation, and that's the product they showed. It was 2 steps. B and C. From there, they continue to build the structure. I'm sorry, that's not Zoloft, that's Paxil. Very similar to Zoloft. I said Zoloft earlier. Okay, there's the puzzle again. Okay, so we saw oxidation of alcohols there and oxidation of some oxidations of alkene. Any questions in that handout? Did we cover everything there?
I had a question on the
Workbook, what page?
5.
Workbook, page 5. Which number?
Number 2, under extra NMR questions.
Number,
Number 2, under extra NMR.
we looked at this before, I thought.
It's probably that.
Number 2,
Yes.
A and B. Did we look at this before?
Yeah, it was early in the morning, Friday, when you held the review.
Review session, okay, question?
I just understand why one of the methylene H's wears the same, but why another one is different.
It's a tetrahedral carbon, so one H is forward, one H is back, because the other 2 are drawn in the plane. This H is going back. It's between the two bromines going back. So it sits between, okay. The H is back there, the two bromines are back there, so it's sitting between those two bromines. The other H is not sitting back there between two bromines. It's forward. And so that's a different position. Both bonding positioning and space positioning, both of those influence NMR.
So it's the same on the other one because they're both between the bromine and
Over here, one H is back there between a bromine and methyl. The other H is forward between a bromine and methyl. And so they're in the same chemical environment. And so the drawn in H's for B are the same, that's one signal. But over here they're different. Number of signals, these two H's are the same in both. Because that's planar carbons, okay? I mean, those are the same. And the two methyls are the same. This methyl is beside a bromine. That methyl is beside a bromine. This methyl is beside a bromine. That methyl is beside a bromine. I mean, yes, one methyl is back, but it's also beside a bromine. It doesn't matter if it's this and this versus this and this. They both are the same. I mean, it's like this. Black compared to green. How about now? Is that any different? Black compared to green, it's just kind of flipped, I mean, right? You see it? Yes. We did a couple like that in through the worksheet. Where it's actually two H's on the same carbon. But they're different here. That's for tetrahedral nature, but we've also seen that, for example, here. There's three H's there. How many signals for the three H's? Three signals. Each H is different, right? This H is cis to the chlorine, that H is trans to the chlorine. Those H's are different. This stereochemistry comes from the double bond. That stereochemistry comes from the ring being like a rotation and tetrahedral nature. That's A, B, and C. Two H's are different. With these, though, I mean, you have to maybe think a little bit more. Because the tetrahedral nature, kind of visualize a little bit more and see exactly more what's going on. Where this is probably much more straightforward. Let's look at some multi-step synthesis in the epoxide handout, I believe it was. Provide a synthesis of the following, starting with bromobenzene. We did the second one. How about this carboxylic acid here? Okay, the main functional group here is a carboxylic acid. Do you know any way to make a carboxylic acid?
Yes. You reduce an alcohol, or primary alcohol.
Not reduce it.
Or oxide it.
Oxidize primary alcohol. Yes. We now have a new reaction for your toolbox, right? Do you know any other way to make a carboxylic acid? So you're from an alcohol. You actually know another way. What's another way?
You can cleave an alkene.
Cleave an alkene.
Cleave an alkene
Okay,
with
and then-
oxidation of maybe to an aldehyde and then oxidize the aldehyde. So two different starting materials. We can start from an alcohol or an alkene.
Is one answer wrong? Because what if you do the whole thing with one and it was wrong? You have to like start all over with the other, then you've lost it all at that point.
Well, you said, what if you do it all and it's wrong? If you do it all and it's wrong, then it's wrong. But if you do it all and it's right, then that's fine.
Well, how do you know which one to choose is what I'm saying. Because what if you choose one direction on the test and you've gone down this rabbit hole and you've lost all this time and you should have chosen the other one? So how do we distinguish which one to choose?
Okay, well, I'll tell you this. Think about efficiency and so-called atom efficiency. Cleaving an alkene, while it's good and it's useful, the drug synthesis use it, they probably do that on commercial. Cleaving carbons is usually not the most efficient. You're actually going from a larger molecule to smaller molecules. Usually you want to go the other way. Usually you want to start with small things and build it larger and larger. So the cleaving of the alkene is not really good in terms of atom efficiency. That's sort of a term. Okay. That is, if we were going to do that, we would have to have these 8 carbons. The alkene would have a 9 carbon. Be at least one more carbon. But look where we're starting from. We're starting with 6 carbons. Why would you want to go from 6 to 9 and then cleave one to go back to 8? Now, you theoretically could. But that's the idea of sort of building your molecule up. The better route is from the alcohol. So let's go back here. We go back to what?
Bromine, but do a Grignard reaction.
No, Grignards don't give carboxylic acids. We go back one step at a time.
Oh.
We need it.
All right? What one reaction would give that? What do you want to draw here that we can then react to give this?
A
Primary alcohol with like.
Yes. We go back to the primary alcohol. This is retrosynthetic analysis. Okay? One step back at a time. This is how you should be doing synthesis. Yes, I am. Thank you. Very good. Rookie mistake. 2 carbons. We actually want 2 carbons. Yes. If we had this alcohol, could you then convert it to this?
Yes.
What would you use?
A big
Chromium
series.
oxide.
One of the big 3. How about chromium trioxide and with sulfuric acid? Yes. Now the problem becomes, how do you synthesize this? Because if we can synthesize this, then we know how to get home from there. Now let's start here. How do you make this?
You have like
Nucleophile carbon-carbon OH. We can back this up to this anion, which I don't want to, may not necessarily be a free anion, but again, this is how we react these, plus what? Would that anion react with that epoxide to give that product? Maybe after appropriate workup?
yes.
Yes.
Yes, and this is going to be more in the form of what if we showed an exact reagent, right?
It'll have magnesium.
Phenyl, magnesium, bromide maybe, right? Benzene anion, bromine anion, Mg2+. But this is essentially this, phenyl being benzene, okay? Because these would react to give this with workup. because that's where the protons would come from workup. Right? Tack here, kick that off. So we make that bond, kick off the oxygen anion. Workup supplies the proton. So basically we need phenylmagnesium bromide with this. That's the simplest of epoxides. It's got a nice, neat name. Anybody know the name of that? Alkene. What's the name of that alkene? Simple. It's actually called ethylene, but I thought you might say ethene. Ethene, propene, butene. Ethene. Well, ethene, the slang for ethene is ethylene. Somehow it picked up an L along the way. Ethylene. That's ethylene. You can polymerize it and get polyethylene. We can convert this maybe with MCPBA. By the way, we don't really need to do this for the synthesis because all we need to do is start with bromobenzene. If you start with bromobenzene, you can use anything else you want. The only reason I'm showing you this is because we put an oxygen on ethylene. This is actually called ethylene oxide. Don't need to know that, but it just makes sense, right? Oxide is like you add an oxygen. Yeah. You see 100, 150 years ago when scientists, chemists made things, all they knew was, hey, we added oxygen to our ethylene. And when you add oxygen, it's now an oxide. And so that's where those names came from. Ethylene oxide. So ethylene oxide is the simplest epoxide. You would not have to show this for your synthesis. As long as we can go back to bromobenzene. Are we back to bromobenzene? Yes, because if you take bromobenzene, draw your big line here. You react that with what?
Grignard.
Magnesium metal. Make your Grignard. Then you come in with ethylene oxide. And with appropriate workup, you'll get your alcohol. Everybody there? And then from your alcohol, you oxidize it up to your carboxylic acid.
Can you bypass the alcohol? You know. Why don't you have the alkene attached to the epoxide that you could react with the chromium?
Have an alkene attached here?
Yes, sir.
Like, what do you mean?
Yes, so like this with another alkene attached to that.
Off here?
Yes, sir. And then the electrons that are sitting with the bromine and magnesium attack and kick off, attach and bind to the epoxide, breaking into the alcohol, and with proper H+ workup, get rid of the alcohol, but you'd have to react.
You're going to have an alkene here, right?
Yes, sir. And then get rid of the alcohol, and then you could react it with the chromium to reduce it to the.
No, reacted with what?
With the chromium and the oxygen for the oxide. No, I'm sorry, for the carboxylic acid.
I'm not sure that chromium will cleave an alkene.
Oh, I was thinking with ozone, and that wouldn't go all the way to the carboxylic acid.
It could, but I don't know how you're going to get rid of this alcohol.
Yeah. Okay.
Because this is going, if this is here, it's going to oxidize to a ketone.
I think it was if you did an H+ workup before with the alcohol to get rid of it, would it just leave?
Yeah, but that might react with the alkene. I didn't think about that.
You got to be careful with your H+ workup. It's cold, dilute. You don't want to be doing chemistry with your products with your H+ workup. I mean, you could, but H+ workup is just enough to get the proton run.
Okay.
You also have too many carbons here because you cleave this, you're going to have 1, 2, 3 coming off the side chain. We only want 2 carbons coming off the side chain. So you really maybe want alkene here.
But that would be resonance stabilized once you.
Just not needed.
Okay.
Now, you could do whatever you want as long as it works. I mean, this oxygen is what you, from there, the alcohol can just be oxidized up, and it's like, you know, it's like if you want to, the straightest is often a straight line. The shortest is a straight line.
Okay.
Okay, but again, you can get creative, and I can look at it and say, hey, you got 12 steps here. You could have did it in 2, but your 12 steps worked. You just wasted a lot of effort, time, and ink, and it's creative. Okay. And as we go along, there may be, you know, once we get to the end of the course and we do synthesis, we may come up with 3 or 4 different routes as our toolbox gets bigger and bigger. As long as you start with bromobenzene and all your reactions work, then you're going to be good. How about the ones below? We did the 2 in the middle there. Can we do the one below, first one? We didn't do this one? We just did that one? How about this one here from styrene? Okay, but let's not worry about styrene right now. Let's, how do you make, main functional group here is an ether. You're not going to make a benzene ring. Ether, how do you make ethers?
Williamson's
We'll back this up to what?
Probably.
Alcohol? Still good?
Why wouldn't you back it up to an alkoxide? Iron. With a minus on the O.
Well, we do need a minus. If we came forward, how would you make this from this alcohol? You'd first react it with sodium metal, maybe? Make the anion, the alkoxide, then what?
With like methylbromine or something.
Or methyl iodide?
Iodide.
Or dimethyl sulfate, like was used on the drug example? Why iodide here? Who said bromine?
I did. I just.
Methyl bromide's a gas.
Okay.
Theoretically works. Methyl iodide's a liquid, and thus much more common to use the iodide with the methyl. You probably never going to find methyl bromide in the lab. Methyl bromide is used as a fumigant because it's very reactive. They go in and spray warehouses, kill all the rodents and roaches and stuff. They'll seal it up. In the lab, the iodide here, because it's a liquid, pretty volatile. You don't want to be breathing it. Alkylating agent. Everybody good there? Williamson ether synthesis? Alcohols. Alcohols from epoxides. That's a key thing for this material here, yeah? Nucleophile carbon-carbon OH. How about this here? Back this up to basically the oxygen bonded here plus ethyl anion. We had the ethyl anion plus the epoxide. Would that give this product would work up? Yeah? These electrons attack here, kick that off, make that bond. Yeah. Now this is really like ethyl magnesium bromide or chloride, right? That's what that is. Grignard. Or you could use ethyl lithium. Basically, we can back this up to the epoxide. Everybody with me? Nucleophile, carbon. So how would you make the epoxide?
Keen with MCPD.
Styrene, okay. Styrene. And MCPVA. So you convert styrene to the epoxide, you react it with an ethyl anion, either the Grignard or ethyl lithium. We work up, it gives us alcohol. And then from the alcohol, you convert it to the ether you want within the Williamson ether synthesis. Yep. Anybody have this already done? Got an alkyl chloride here. How do you make alkyl chloride? Ever made one?
You can react it with an alcohol.
So, yeah, react what with an alcohol?
You know, react an alcohol and HCl.
React an alcohol with HCl. All right. Any alcohol?
Secondary, it'd have to be a secondary alcohol.
Second and tertiary is going to be best because HCl is going to be an SN1. What if it's a primary alcohol? What would be a better reagent? PCl3 or thionyl chloride. Those activate the oxygen more and more prone to be an SN2. Okay, so back this up to what? By the way, let me go back to the previous one At this point, how do you make alcohol? Well, opening an epoxide. We could have actually come back to an alkene. Because if you have the alkene, can you convert it to an alcohol? Yeah, you can. I mean, that's an organic one reaction, hydrate the alkene. Problem is, how are you then going to make the alkene? Alkenes are often made from alcohols, by dehydrating alcohols. This is where you can get in a never-ending cycle. You're like, okay, well, I'll make the alkene from the alcohol. So you take the alcohol, convert it to the alkene, and then you hydrate it back to the alcohol? Then that don't make any sense. So it's the power of the epoxide is it allows you to bring together two organic fragments. They can both be huge. You need to break the carbons apart, and that's what the epoxide allows you to do. You're making carbon-carbon bonds. This is just not going to get you. All right, let's go back over here. How do you make alkyl chloride? We had the alcohol. Could you convert it to the alkyl chloride? What would you use?
HCl.
HCl, yeah. That may very well work here. It's a benzylic carbocation we're looking to form. Protonate, ionized, chloride attacks carbocation.
Could we use PCl3?
PCl3 would work as well. Again, what do we need to start with? Styrene. At this point, it's no different than the previous one. We've got an alcohol. It's just a different alcohol. The only difference is this can actually be backed up to that epoxide plus what? No, missing a carbon. See, when I connected that, the carbon disappeared. Nope, I'm wrong again. I don't need an extra carbon. What do I need to make here? I need to make that bond. Carbon-carbon, nucleophile carbon-carbon OH. I need the original. I just need an isopropyl. I Isopropyl carbanion there, right? Carbanion. This attacks here, electrons up. Work up puts the H on, and then I can react with HCl. Yeah. Let me look at it a little bit later. We're about out of time. Grignards don't do SN2 that well. Although this is an SN2. Grignards react with epoxides nicely. They don't do more traditional SN2, kicking off halides as well. Okay, guys. I'm not sure we're ready for test on Wednesday, particularly NMR. I think we moved the test to Monday. Week from today. Wednesday and Friday, we will begin test 2 material. I don't like to have tests on Friday, so we're going to move it to Monday. Okay? Wednesday and Friday, we're going to begin test 2 material. Okay? I'll give you another week for NMR. Test on Monday will include comprehensive NMR. I posted a video yesterday on working some problems. Okay. See you Wednesday, yeah? Lab this week, based on your student number, right?
I have a lab for it, and then I have lab.
Okay, yeah.
It's a good day. This is a great start. So much better.
Oh, you probably could have done it. I think I got 2 of those, right? I got close on all 5 of them.
You just want this to come in. Grignards don't do
Yeah.
So, you also recognize yeah, so it's a little bit, yeah, I don't know where I got that. That's no problem.
I'm like, you mentioned an 80.
You just convert that to, that's why I didn't write down iPhone. We got the same thing.
Here's what I did.
Just in practice. I mean, that's what I wrote. But we got the same. We got
How did you get that?
in practice.
Write down meaning. Well, maybe this will fit in somewhere.
But yeah, theoretically, you gotta do
What's
this.
the big fucking 44 plus 50. That's 80. Did you do like 100 minus 50? You take the math wrong? No, I just went over 100 minus 50. Well, that's not very